Okay, Trig students, today we're going to get a basic introduction to vector operations, and next time we will, or actually in class and next time, we will start applying some of these trig operations to these vectors to start to figure out directions and different parts of vectors. So as we get into the brief introduction here, we'll talk about the vector quantity. A vector quantity is any quantity that has what we call both magnitude, which magnitude in a sense means size in this case, and direction. Okay. Whoops, that should be an O. I'll erase that so it looks nice. Both magnitude and direction. So that is a vector quantity. Now a vector will be what we see as a representation. So it will be an arrow which will be representing a vector quantity. The length of this arrow represents its magnitude, or its size, its magnitude. And the direction of the arrow represents the direction of the vector. So for some of you, most of you this won't be an issue, but for some of you this may be. We really need to be clear on our directions. So look over here real quick. Draw like a little, what looks like a little coordinate plane here. Okay, like a compass. And what we need to establish here is that we understand that on paper, up represents north and down will represent south. On paper, right will represent east, and left, let me make some room, will represent west. That will be important as we start applying these real-world applications to these vectors. Okay. Knowing that, what I want you to do is on your own look at these vectors right here. Okay. It's just an arrow will represent that vector, and I want you to describe down this line what you feel like this vector represents or what it means. Okay. So go ahead and hit pause and do that real quick. Okay, now that you're back, hopefully, since our vector was going in this direction to the right on our paper or on our screen, I hope that you recognize that this implies that something is 40 miles east. Okay, or something traveled in that direction 40 miles. You know, I'll get specific over here and actually make something up, some scenario. Not that I expected you to do that. I expected you to say, you know, something was going 15 miles per hour southeast. Okay, so let's just say, I like the name Hank. Hank was, or is, biking at 15 miles per hour, heading southeast. Okay. Now when we say southeast, we mean exactly southeast. Alright? So that means halfway between south and east. Okay, that's important to know. Alright. Now vectors are going to be labeled from what we call the initial point. Okay. And they are going to end on the terminal point. That should kind of ring a bell with you with our initial side and terminal side with an angle. And we are going to name them with 2 letters or by 1 lowercase letter. So, this vector right here, we would say would be, when we label it, we would say it's vector AB. This vector here would be vector V. So you can either label it with 2 uppercase letters or 1 lowercase letter as you see fit or as it applies to the problem you're working on. Now, equivalent vectors are 2 vectors with the exact same magnitude meaning the same size and the same distance or direction, I'm sorry. Direction. Okay? So just because 2 vectors have the same size or magnitude does not necessarily make them equivalent vectors. In order to be considered equivalent, they have to not only be the same magnitude or size, they also have to be going in the exact same direction. Okay, so that's important to note as we move forward with our vector lessons here. Okay, let's move on to the next page. Talk about vector addition. Okay. Vector addition isn't really, we're not just adding together numbers. Okay. Vector addition, if we're given 2 vectors, let's say we call them u and v, you can find their sum, okay, which implies vector addition, or we will call that the resultant vector by using either of the 2 methods below. Okay. Now, these methods will show that vector addition is commutative. Commutative in nature. Alright. So the first form is the triangle method, and there will be certain instances that will be better to use one method or another. Okay. The triangle method, you're going to place the initial point of v at the terminal point of u. So if I'm taking u plus v, well, we know that that equals v plus u. But if I'm adding them together, you're going to take the initial point of v, meaning where vector v starts, and you're going to start vector v at the terminal point or the end point of u. Okay? Now, what people are tempted to say is, well, u plus v is just going to be this length plus this length. That is not correct. Okay, those of you who have had physics will understand that when we're talking about vector addition and our resultant vector, we are talking about displacement here. Okay? U plus v is not actually the sum of the 2 sides. It is, okay, u plus v is the vector from where we originally started over here on vector u. Okay, so from the initial point of u to the terminal point of v. So here's how you can kind of think about this. When I'm doing vector addition, I'm talking about where I started, the distance from there to where I ended in that direction. I'm concerned about that direction and distance. So, for instance, let's say you were at the high school and you walked to Jiffy Stop and then you walked to McDonald's. Okay? You wanted to get a soda at Jiffy Stop and a sandwich at McDonald's. Don't ask me why, that's just my example. Well, you walk to Jiffy Stop, then you go to McDonald's, but what we want to know, we don't want to know the total distance that you walked. We want to know how far in the direction it would have been if you would have started at the high school and just gone straight to McDonald's, where you ended up. Okay? So that's kind of how vector addition works. So let me go ahead and draw this resultant vector here. Let's see, should be there. And when I draw that in, okay, that is what we talk about as being u plus v. So again, it is not the vector u, like the distance of that plus the distance of that. It is, we're talking about the displacement from where you started to where you ended up. Okay. Now there's also a parallelogram method, and the parallelogram method will come in handy in some certain instances as well. You're going to form a parallelogram with u and v. Okay, so same vector u and v, but you're going to do that as adjacent sides. So adjacent, starting from some common point. Okay, so if you knew that this was u and this was v, then u plus v extends from that original point to the opposite vertex. Okay, now you get the same thing that we got up here, right? Only this is going to, there's going to be some real world applications where this is a more usable method. It will make more sense to use that. So what's going to happen here is when you draw that, so I know I've got u and I've got v, then I'm going to draw a v off of here as well, and a u to right over there. And when I draw that vector from where I started to the opposite vertex, and that is u plus v. Okay, u plus v. Alright, so hopefully you understand that when we are doing vector addition, just remember, it is not the sum of the two distances. It's talking about the distance that we have displaced from where we started to where we ended. Alright. We'll look at, if you would, I've got, this is going to be your oral exercises, and you're going to get assigned 1 through 16 on the oral exercises. I'd like to show you a couple of them just so you get an idea here. Okay, so and I believe that number 1 on the oral, and you don't have to do all these, but I'm going to go ahead and show you so it will help you out understanding the process you'll need for your daily problem as well. Okay, so if you look at number 1, I believe that number 1 says dc plus cx equals dx. So dc plus cx equals dx. Okay, so let's go check and see if that is in fact true or false. Well, I'm going to grab a highlighter here. Yeah, that'll be all right. So DC, well, DC runs in this direction right here, right? And then it says plus CX. Well, that works out good because CX is right here. Okay. So what is the resultant vector? Where did I start this process? I started this process right here. I ended this process right here. So when I'm looking at a resultant vector, I go from where I started to where I ended, and what vector is that? dx. So is that true or false? Yes, it would in fact be true. Okay? Now they won't all end up perfect like that. You know, that you may have to, it may have said dc plus bx. Well, then you kind of have to think in your head or draw on your own a vector bx up here from the dc. If it was dc plus bx, I would go d to c, and then I would have to draw a vector that is equivalent to bx from right here. So it would have gone up in this direction, right? Okay. And then I would look for that resultant vector right there. So anyway, number 11 says well, let's see. I think, and I don't have my book in front of me, I apologize, I just have my notes down. So, what is 2 times xd? Okay, so what I would like to do, let's figure out what that is. 2 xd's. Well, if I had an xd, okay, if I had an xd, I'm going to go to another highlighter, make it a little thicker here so we'll cover that up, make it green, and xd would be going in that way. And then if I had another xd, okay, so I would have another, I would start here at the end, and then I'd keep going that way for the same distance. Well, that is equivalent to what vector that is on this drawing right here. I would be going in this heading, in this direction, right? And it would have to have the same magnitude or the same size. Is there a vector on this drawing that has this direction and has that same length? Well, in fact it does. It would be BD, right? Okay, so that's kind of how you need to look at these vectors. We'll have a daily problem when you come into class. We'll do a little activity and work on some problems. And we're going to spend some time on these vectors and apply them to certain aspects and be more activity based here for another week or two, so when you get back. Alright, have a good weekend. Bye bye.